Okay, in the last class we have been discussing about the attitude dynamics. So, we continue with that, and in that particular part we were discussing about the moment of inertia matrix or the inertia tensor. So, in that context we have been working out the properties of a real symmetric matrix. So, we saw that our inertia matrix or the inertia tensor is a real symmetric matrix, okay, and therefore, all the properties of a real symmetric matrix is applicable here. All the properties of a real symmetric matrix are applicable. So, we wrote the inertia dyadic as I alpha beta times E cap alpha and E cap beta, and in that what we wrote as this I 1 E 1 cap E 2 cap I 1 2 E 1 cap here, and I 1 2 E 1 cap E 2 cap and so on. So, here in the next we had the I 1 2 E 1 cap E 2 cap and then I 2 2 E 2 cap E 2 cap, so on. And the last entry here is I 3 3 E 3 cap E 3 cap, and moreover as I told you that here a minus sign you can absorb in this place. If you absorb the minus sign, so what we need to do, we can put here also the plus minus sign. So, plus sign plus when alpha equal to beta minus when alpha not equal to beta. So, that way you will be able to absorb the negative sign in all these places. Okay. So, only with the diagonal elements we have the positive sign, and with the off diagonal terms we have negative signs. So, here in this place we have I 1 3 with a minus sign here E 1 cap E 3 cap, and we are putting a minus sign here in this place, and then we will have I 2 3 E 2 cap E 3 cap with a minus sign. So, now we are going to discuss about the principal moment of inertia. The inertia tensor of the body through the center of mass So, we have the inertia tensor of the body for a set of axes passing through the center of mass, and So, inertia tensor or either inertia dyadic and axis parallel to the unit vectors E1 cap, E2 cap, E3 cap, is defined as and as I told you that for the off diagonal terms, if you want to remove use the sign in the for the order off diagonal terms as negative. So, you can put here plus minus sign, though this notation is not very usual, but this makes it convenient in this case, and this notation becomes uniform with the other notations which are available in the literature. So, here alpha equal to 1, 2, 3 and beta also equal to 1, 2, 3. So, if we are writing just inertia tensor, means inertia tensor is you can write as I11 minus I12 minus I13 and so on. Okay. While we are talking about the inertia dyadic, so in that case you need to put here. So, for inertia dyadic we put a double bar over this and then you need to put here I11 E1 cap, E2 E1 cap, then I12 and you can put a minus sign here as we have discussed here. So, E2 cap, E2 cap and so on. So, this is the difference between these two. Here the vectors are also included, while in this the vectors are not included. Thus, the components of the inertia dyadic form a real symmetric matrix So, here we are talking about the magnitude part. And this is a 3 into 3 matrix. And therefore, all the properties discussed in the last class now the eigenvalues of the inertia tensor are called the principal moment of inertia. And the eigenvectors of the inertia matrix are the principal directions. Like you can consider it in a way, say this is your body in which you have set a body x at the center of mass, where you are showing the E 1, E 2 and E 3 x, and the unit vector in this direction is E 1 cap, E 2 cap and E 3 cap. These are the unit vectors. Now, say your principal moment of inertia. So, for a real symmetric matrix, you will get 3 values for the 3 eigenvalues. You will get 3 eigenvalues. So, they are indicating the 3 principal moment of inertia, and the corresponding eigenvector will tell you the direction of the principal moment of inertia. So, say that you show one direction like this, another direction like this, another direction like this. Okay. So, this is your principal moment of inertia. Now, instead of writing I 1 we are writing as 1 to indicate this is the principal moment of inertia, I 2 and I 3. These are the 3 principal moment of inertia, and they are directed along this 3 x. Now, you can see from this figure that the orientation of, say, the I 3. So, the orientation of I 3 can be defined using the angles, this angle from here to here, angle from here to here and angle from here to here. So, defining these 3 angles are required, and let us say that this angle is alpha 3 and this is beta 3 and this is gamma 3. So, angle alpha 3, beta 3 and gamma 3 are required to fix the direction of the I 3. So, I 3 is the moment of inertia and its direction is directed here, and you need at least 3 angles to fix this direction. So, similarly, you will have to define the angles for. So, these are your fixed sets. Okay. These are the body axis which you are fixing in the body, and this can be chosen arbitrarily. And in this case, the center point we have chosen as the center of mass. If we choose another point as the center of mass, so about that point the principle of moment of inertia will become different, its direction will also change. Sorry, the principle of moment of inertia direction will differ if you choose any other point. We are considering here, and if we take another point, and about this point if we try to find out what will be the directions of the principal moment of inertia, they will be totally different. And similarly, the directions are different, and also the moment of inertia, principal moment of inertia value will also change. Okay. So, here I am not drawing the lines not to complicate this figure. So, to start with, this is our figure. So, one thing you should remember here, that what I stated, the principal moment of inertia and its direction changes if we change the point of consideration. That is very obvious that whatever the inertia you are having about this point, you cannot have this point. That is similar to say that if you are taking the moment of inertia about this x, which is the we are choosing first the point here, and then we are measuring the moment of inertia about 3 perpendicular x. One x is this and this. Okay. And if you instead of doing this, if you choose the point here and you have the directions like this. Okay. So, obviously, at these 2 points the moment of inertia will not be same. So, moment of inertia along this 3 axis will be different, and here it will be totally different from here, and correspondingly the moment of inertia, principal moment of inertia also changes, principal moment of inertia and its direction changes. Okay. So, here the principal moment of inertia will be something else, and at this point the principal moment of inertia will be something else. Direction in this at this point for the principal moment of inertia, as we have shown here, it will be different. At this point also this will be different. So, the eigenvectors are the principal directions as we have written, and the fifth point we have discussed here. This was the fifth point, that as the point of consideration changes, the principal moment of inertia and its corresponding directions also change. Now, how to work out the principal moment of inertia? So, the angular momentum vector, if you remember, we have written as, or the in matrix notation, the same thing, H 1, H 2, H 3. This can be written as omega 1, omega 2, omega 3 and I 1 1. So, in other words, what we have done, that H can be written as, this is what the notation we have written in terms of inertia dyadic. So, this is your angular momentum vector. So, in general, the H vector and omega vector do not coincide. So, H is equal to I double bar omega. In this H vector and the omega vector, they are not the same. They will be pointing in the same direction, if the inertia matrix tends to be a proportionality constant. And in that case you can write H is equal to say some I c, this is the to indicate this is a constant times omega. So, in this case you can see that this is just appearing as a proportionality constant, and therefore, H vector and the omega vector they are pointing in the same direction. So, H is a vector here, to indicate we can write H is as a vector here in this place, and I is the inertia matrix and omega is a vector. So, to find out the principal directions we can write this as lambda omega, okay, where now lambda is indicating a quantity by which if the vector is multiplied, okay, this will be equal to this, and this will happen. So, you can solve this problem. So, if you solve, so you have the inertia matrix here I 11 minus I 12 minus I 13 omega 1 omega 2 omega 3 and this times lambda, and this is omega 1 omega 2 omega 3. So, bring it on the left hand side. So, this whole problem can be indicated as I 11 minus lambda minus I 12. Okay, it is a very easy doing this. Omega 1 omega 2 omega 3, because you remember this product, this is a 3 by 3 matrix and this is 3 into 1. So, this is a vector and here this also is a vector, and therefore, you can subtract. So, what you need to do, just put this in a in the form of a matrix like lambda 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 of diagonal terms being 0 and this multiplied by omega 1 omega 2 omega 3, okay, and the subtract on this side. So, basically you are multiplying with the identity matrix. So, if you multiply with the identity matrix you change nothing in that. So, this matrix is equivalent to this vector multiplied by lambda. So, no difference. Now, you subtract it. So, this will quantity will turn out to be 0 on the right hand side. So, I 22 minus lambda minus I 23 minus I 13 minus I 23 and I 33 minus lambda. Okay. So, for now this is 35 7. Now, for non-trivial solution, the determinant of I 11 minus lambda minus I 12 minus I 13 this must be equal to 0. So, now we can determinant of this matrix must be equal to 0. So, expand it, and by expanding we can solve. So, we can write here lambda cube Okay, this is what you get. Okay, solve this. This will give you 3 real roots. So, by solving this equation, we get 3 real roots, which are the principal moment of inertia. Okay. So, these 3 roots are our principal moment of inertia and the corresponding eigenvectors, and the corresponding eigenvectors are the principal directions. So, in this equation that we wrote earlier, I 1 minus lambda, and let us put here instead of lambda now the lambda I, this is minus 1 2 minus 1 3 minus lambda I minus 2 3 and then omega 1, we put the subscript I, that is the eigenvector corresponding to the ith eigenvalue. Okay, now, this matrix, this is singular. What does mean by singular? Singular implies that the determinant of this matrix will be 0, and for the non trivial solution, that is what we did here. We found the determinant of this, equated of determinant of this to 0, and then worked out the principal eigenvalues. So, if this is a singular matrix, so obviously you cannot solve for omega 1, omega 2 and omega 3 simultaneously. Only 2 of them you can find, and third is to be fixed, because the third equation will turn out to be a linear function of linear combination of the other 2. You can say in another way that these 2 can be combined to give you the third equation, third line here. So, now this is the situation. So, in that situation, how we will find the principal moment of inertia direction. So, as I explained you earlier that the principal moment of inertia direction, these are the 3 directions which are available to us, but one favoring thing is available, that cos alpha I a square plus cos beta I a square times cos gamma I a square, this will be equal to 1. This is follows from, this is the cosine property. So, these are the direction cosines. So, a square of them will turn out to be equal to 1. So, now if we impose this condition, so you will be able to fix the third direction. Okay. So, it is telling that here that only 2 can be worked out, only 2 elements omega 1 I and omega 2 I can be worked out, and 3 I cannot be worked out, because basically this is singular. So, to fix it up, if we assume that this is to be followed, then the whole thing gets solved. Okay. So, now let us see that how to write in the form of cos alpha I, cos beta I. Okay, so we have to find out the angles here alpha I, beta I and gamma I. Okay, so to find out the angles, we go back into our original picture. E1, E2 and E3, these are the body x direction, this is the center of mass. Let us say that this is the principal inertia I3 and this is the corresponding direction. We need to work out these angles. I will write this as alpha 3, this angle as beta 3 and this angle as gamma 3. Now, these are the three angles we have to decide, and these three angles give the direction. So, the matrix that we have used I11 minus lambda I minus I12 minus I13 and instead of using here the eigenvectors as omega 1, omega 2, omega 3, not to confuse with, because this notation may confuse. So, let us choose here as omega 1 I, which is corresponding to this particular ith eigenvalues. So, this is the corresponding eigenvector I 2 I, A 2 I and A 3 I. So, we can disassociate with the omega for the time being. Okay. So, this quantity equal to 0 and we have seen that this is a singular matrix, and therefore, only two of them, two equations will be independent. If we form the equations, three equations you can form here, but only two will be independent, one will turn out to be a linear combination of the other two. So, that simply implies that only two of them you can find out independently. Okay, so, for the third one you cannot solve. So, in this case we assume the third value. So, we assume A 3 I, or say you can assume A 1 I. So, in this case let us say that I am assuming A 3 I and then solve for A 2 I and A 1 I. So, once we solve for this, so now after fixing this value p, you have the particular equation coming from here, lambda is known to you. So, you can fix this value and solve the equation. After solving, you can solve the other two also. Okay. And thereafter, what you need to do, that you square A 1 I, A 2 I square and A 3 I square, take the square root of this and write this as, let us say a quantity which is delta. So, if in this equation, if I divide by a quantity delta, it will not affect the whole thing. This is very obvious from here, where delta is a non-zero quantity. Okay. So, this delta we are using, and if we divide it by A 1 I divided by delta, okay, so this we can write as cos alpha I we have used. Similarly, A 2 I divided by delta we can write as cos beta I, and A 3 I divided by delta, this we can write as cos gamma I. Now, you can check that by squaring these quantities and adding, this will give you 1. So, ultimately you are going to get cos alpha cos square alpha I plus cos square beta I plus cos square gamma I, this is equal to 1. Okay. So, you have done basically the normalization of these quantities. So, in the normalized form, this is what will appear. So, A I gets A I 1, the value you choose the value A 3 I. So, here let me write choose the value A 3 I and find A 2 I, A 3 I, A 1 I. Okay. Then normalize A 1 I, A 2 I, A 3 I by writing A 1 I, you will be replacing by A 1 I divided by A 1 I square plus A 2 I square plus A 3 I square under root. Okay. Similarly, A 2 I you will be replacing as A 2 I divided by A 1 I square plus A 2 I square plus A 3 I square, and similarly A 3 I you will be replacing with A 3 I divided by A 1 I square plus A 2 I square plus A 3 I square. So, these three quantities, they are nothing but your the cosine quantities, cos alpha I, cos beta I, and this quantity is cos gamma I. So, once these values are known, means your these three angles get located. So, this way you have located the one principal direction, the I 3. So, in the same way, you can choose the next direction. So, we can choose the next direction here, let us say this is your I 2, okay. And similarly, then you have to work out for all these angles. So, here now this angle will be your beta 2 and this angle will be gamma 2, and the angle from here to here, this will write as alpha 2. And then finally, you may have I 1 in this direction. So, this I 1 also you need to fix it up. So, here you will have this as alpha 1 and which is the direction angle from E 1 and measured up to I 1. Then you have this angle as alpha 1 beta 1, and with E 3 the angle made this angle from here to here, this is your gamma 3. Okay. So, by following the procedure that we have just described, it is a possible that all the angles you can write here. Okay, once we have done this, so a very simple example can be taken up. Let us say this is a cuboid and these are the body x that we have chosen, E1, E2 and E3. This is the point O. Okay. Now, this point is obviously not the center of mass here in this case, and we need to work out the moment of inertia, principal moment of inertia. So, finding out the principal moment of inertia, first you need to write the inertia matrix. So, for writing the inertia matrix, you have to get all these quantities I11, I12, I13, so first we need to work out these quantities. So, I11 we can write as x2a square and x square plus sorry, this is y square plus z square times dm, okay, and integrate it. Okay, so, we are going to develop these things later on. We have still not developed how in the angular momentum equation this term comes, but the I11 term can be written as this. So, once we know that, let us take it for granted that this term is being written in this fashion. So, once we have taken it up, so dm can be written as along the three different axes. You have we have E1, or here let us say this is we write as x y and this as the z. Okay. So, dm you can write as rho times dx, dy and dz, okay, where this quantity is the density and this is a constant, means it is a uniform density material you are taking. Okay. So, it is not varying along the three axes, rho is constant throughout. Or the same thing you could have written in terms of, if you write in terms of say the r as r1 square, r square, r2 square plus r3 square, okay, which are the component along the E1, E2, E3 axis. So, you can also write the same thing, instead of using this you could have written r2 square plus r3 square, and you could have developed the whole thing. So, let us follow this. So, once we do this, you can also term this as I x x. So, inserting this into this place, y square plus z square, rho will come here and dx, dy, dz. So, here we have all these quantities. So, at least at first we can integrate out x out of this. So, rho we are taking out, and integration we can put in the limits, you can put the limits for all of them. So, integration limit is 0 to a, 0 to a, 0 to a. Okay. So, rho a and y square plus z square dy dz, integrate between 0 to a, 0 to a. Now, let us suppose that we integrate for y. So, rho a 0 to a, this becomes y cube by 3 plus z square y 0 to a dz. And by putting this value, this a here in this place, this becomes a cube by 3 plus z square a dz. So, after integrating this will yield a q by 3 z plus z cube by 3 a and putting z is equal to a and putting these limits. So, what we get here a to the power 4 by 3 plus a to the power 4 by 3. So, this is basically 2 by 3 a to the power 5. Now, rho times a q, this is nothing but your mass of the cuboid. A q is your volume and multiplied by density, this is your mass. So, we can write here that I x x equal to I 11, this is nothing but 2 by 3 m a square. Okay, and by symmetry you can check that I x x equal to I y y equal to I z z equal to 2 by 3 m a square. This is obvious from the symmetry, because it is a cuboid. If had it been a parallelepiped or any other figure, so this result you would not have got. Okay. Next you need to work out I 12. So, I 12 we can write as x y dm, and dm obviously we have written as, and integration limit remains same, x y, rho we can take outside, and this is dx dy dz. So, integration can follow our convenience. So, here because z is not present in the integrand. So, we can take out the z first. So, we can write this as rho a 0 to a 0 to a x y dx dy. Okay. Next we can integrate for y. So, if we integrate for y, this is 0 to a x times y square divided by 2, 0 to a dx. So, putting these values, so what we get here a square x by 2, a square we can take it outside. So, this is rho a cube divided by 2 x dx, and this is 0 to a. So, ultimately this will also yield a square by 2. So, this becomes rho a cube by 4, a to the power 5 by. So, this becomes m a square divided by 4. This is what your I 12, and from the symmetry simply we can write immediately from symmetry we can write I 12 equal to I 13 is equal to I 23 equal to m a square by 4. Okay. So, this is the cross product of inertia. So, your inertia matrix is now available. Okay, so, your inertia matrix is basically 2 m a square divided by 3 So, this is your inertia matrix. Now, obviously, here you can see that m a square is common everywhere. So, for mathematical simplicity we can take out this as common. So, I can be written as m a square 2 by 3 and this is minus 1 by 4 minus 1 by 4 and this is 2 by 3. Okay. Now, this is your inertia matrix and you have to solve for the eigenvalues. So, for solving for the eigenvalues, what we can do? We can work only with this inertia, this matrix here, which are having the numerical values, and whatever the eigenvalues results, if we multiply by m a square. So, result will be we will obtain the required result, or either we can keep it inside itself, then subtract with the corresponding lambda in the diagonal terms, solve it, solve for the determinant. Okay. And there you get the eigenvalues which are the lambda, where the m a square term will be directly appearing. So, both way you can do, but this way obviously working with this is much simpler than looking in other way. So, let us say that we write the quantity which is present here, this quantity as alpha beta beta. Okay, sign we are absorbing inside, this is beta alpha beta and beta beta alpha. Okay. So, this is the matrix now. So, we have to work out okay, we will go one step more ahead. We will write here as 2 by 3 minus lambda minus 1 by 4 minus 1 by 4 and then minus 1 by 4 2 by 3 minus lambda minus 1 by 4 minus 1 by 4 2 by 3 minus lambda. So, in this format, so we have to take the determinant of this matrix and solve it to 0. So, this quantity we can put as alpha and the quantities which are present here, this we can write as beta. So, lambda already got embedded in this. So, we have the matrix now, this is alpha beta beta and then beta alpha beta 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 alpha and set it to 0, solve it. So, if you solve this determinant, so you can write this as alpha times alpha square minus beta square, okay, taking the first term and then alpha square minus beta square plus beta times, then we have this term beta square, this is okay, the mid between we are taking. So, square minus beta square so beta square minus alpha beta and the third term with respect to this we write as beta square minus alpha beta plus beta square minus beta times beta square minus alpha beta, and this is equal to 0. Solve it, and once you solve it, what you will find that you will get this equation, and look, this gives you alpha equal to beta, and this will yield you alpha plus, okay, this will yield you alpha square plus alpha beta minus 2 beta square equal to 0. So, alpha will be equal to either beta or minus 2 beta. So, you have got these three quantities, alpha equal to beta or beta minus 2 beta. So, alpha is nothing but when alpha equal to beta. So, you can see that alpha is nothing but 2 by 3 minus lambda, and beta you have taken as minus 1 by 4. So, alpha equal to beta implies this quantity, and this implies lambda equal to 11 by 12. And then if we multiply it by m a square, so the principal moment of inertia you get as 11 by 12 m a square. So, this is your say the lambda 1 equal to this quantity. Okay. Similarly, we can solve the other ones. Okay. So, here we have the other two remaining. So, this one is alpha equal to beta is lambda 1, this we can write as obviously, here also this alpha equal to beta is coming, and this is the minus beta. So, this is lambda 3, this is your lambda 2. So, rest we do in the next class. Okay, thank you very much.